So I have a calculation here where they're giving me standard free energy of formation values for CuO and Cu2O, and they're asking me to calculate the pressure of O2. Well, at first thought, I can't see how those would be connected, but I do know that this is an equilibrium. And as an equilibrium, we also know that we are going to be able to relate a delta G to a K. So let's write some things down that we know. We know that the standard delta G of a reaction is equal to minus RT natural log of K. And when you're dealing with pressures, you would get a Kp. I also know that if I wrote the Kp expression for this reaction, it would be the pressure of O2 to the 1/2 power. And I wouldn't include these two because they're solids. So I know that if I could get Kp, I could get the pressure of O2 and solve the problem. So how am I going to get Kp? By first getting the delta G standard of the reaction by using the sum of the delta G of formation of products minus the delta G of formation of the reactant. So that would be the delta G of formation of Cu2O plus 1/2, since that's the coefficient, times the delta G of formation of O2, that's the products, minus 2 times the delta G of formation of CuO. So I'll plug in the values that I know to get the delta G of the reaction. For the Cu2O, it's a negative 166.69 kilojoules. For the oxygen, that's the delta G of formation is not given, and it should be known that it's 0. So I'm going to add 0. And then I'm going to subtract 2 times the delta G of formation of the Cu2O, which is a negative 155.2. This will give me the delta G of the reaction equal to 143.71 kilojoules per mole. Now that is a very large positive delta G. If a delta G standard is that large, it tells me that if I were to start with 1 atmosphere of O2, it would go in this direction very far towards reactants. How far would it go? Well, I'm going to calculate my K value now. I have a value for delta G standard of 143.71 kilojoules per mole. I'm going to go ahead and do that in joules. So that would be 143,710 joules per mole. And the reason I want it that way is because I know my R in joules, 8.314 joules per mole Kelvin. That prompts me that my temperature needs to be in Kelvin. It says 25 degrees Celsius, so that's 298 Kelvin, and times the natural log of the K. So I will divide both sides by this portion to leave me with the natural log of K. The natural log of K is a negative 58. So in other words, I am taking 143,710 divided by a negative 8.314 and divided by 298. Now how do I get just the K? I take e to both sides. And this will give me a Kp equal to a very, very small equilibrium constant, 6.44 times 10 to the negative 26. So this also is telling me the same piece of information. Why can't I get my little pen to work here? Oh well, we won't worry about it. There's a little extra line there we'll ignore. So that is a very tiny K. This also is telling me my equilibrium lies far to the left. Now we'll go back up here and remind ourselves what we're trying to determine, the pressure of O2. So here is my relationship that is going to get me the pressure of O2. Kp squared, let me write it this way, Kp is the pressure of O2 to the 1/2 power. So if I square both sides, I will just be left with the pressure. So Kp, which is 6.44 times 10 to the minus 26, squared is the pressure of O2. And when you square that number, you get 4.15 times 10 to the negative 51, and that would be in atmospheres. Now that is a very, very low pressure. As a matter of fact, in any normal container, you couldn't even get one molecule to the right because that would give you a pressure greater than that. Let's see what we can do next, just to get an understanding of how tiny that pressure is. To get a feel for how low that is, let's see how big of a container I would need in order to produce that pressure by only one molecule. So in other words, I'm taking my Cu2O solid, I'm letting it establish equilibrium with my CuO plus 1/2 O2 gas, okay? And we know that it lies far to the left, and we're going to say it's just barely going to the right enough to produce one molecule of this. Question is, how big of a container do I have to even produce one molecule? Well, let's use PV equals nRT. Okay? The pressure we established on the previous slide. What I want to know is what volume would get me that pressure if I only had one molecule. Okay? So we're assuming it's so tiny that, well, let's just see. One molecule. Let's write this. One molecule O2. How many moles is that? Well, I want moles in my equation, right? So molecules is 6.022 times 10 to the 23rd molecules of O2 would equal 1 mole of O2. So 1 divided by Avogadro's number is how many moles I have. So I'm going to go ahead and just write it that way. 1 divided by 6.022 times 10 to the 23rd is how many moles I have. Or I need the one with moles in it, so it's 0.08206 liter atmospheres per mole Kelvin. Temperature, 298 Kelvin. And pressure was that tiny pressure we got on the other side, which was 4.15 times 10 to the minus 51 atmospheres. This gives me a volume equal to 9.78 times 10 to the 27 liters. Okay, that's crazy big. That's how big it would have to be in order to get one molecule to form and it be at equilibrium. In other words, this reaction is not going to proceed towards products.